In order to find the area between two curves, we had to extend the concept of how the height of a rectangle is defined within our integral. Another modification that we could make is to use horizontal approximating rectangles instead of vertical approximating rectangles, and then integrate with respect to dy. So let's take a look at an example where this might be helpful. So here we have an example where we want to find the area of the region trapped between the curves f of x equals the square root of x, g of x equals 3/2 minus x over 2, and the x-axis. All right, so I've already graphed those, and you can clearly see which one's which, because this one would be our square root. So that would be f of x. This one's linear, so that would be g of x. And finally, of course, our x-axis, which is y equals 0. Okay, so the region trapped between clearly is this part right here, which is going to be hard to shade in, but there we go. So that's the region that we want the area of. Now, using what we've learned so far, we could set this up and we could do this. The problem we're going to run into, however, is when we're on one part of this interval, we have a rectangle where the top is defined by our function f of x, but the bottom is y equals 0. And then we reach a certain point. So right here is kind of a separation where we start having the top of our rectangle defined by g of x instead, though the bottom of the rectangle is still y equals 0. So we'd have to do this in two separate integrals if we wanted to proceed. And we could, it's just possibly there's an easier way. And sometimes we need to do this, and it's fairly straightforward to do. What we do is, instead of looking at this as trying to determine the area using horizontal or vertical rectangles, we instead try and come up with the area using horizontal. And here's the advantage. When I use a horizontal rectangle, the top of the rectangle is kind of over here. So I'm going to put that in quotes there, the top of the rectangle. But the nice thing is, on this entire interval, the top of the rectangle is defined by the line, which is g of x. And then down here, the bottom of the rectangle is entirely defined by the function f of x. So here's the thing. I'm going to be integrating dy, which means when I set up my integral, the total area that I come up with is going to be an integral of some function. I'll just say h of y, I should say. Just be careful there. dy, which means, and again, this variable right here, even though it's very much overlooked, is really important because it tells me what kind of function these bounds of integration are. So these are functions of y. So I would be integrating between, in not vertical lines, because vertical lines would be x equals some constant. Y equals some constant are horizontal lines. So this region is entirely trapped between the horizontal line, y equals 0, and the horizontal line, y equals 1. So that's where I would be integrating, from 0 to 1. And on that entire interval, from where y is 0 to y is 1, the top, and when I say top, I really mean the positive part, or the most positive part. So, when I say the top of a vertical rectangle, I'm looking in the positive direction, so the positive y. So here, the top of the rectangle is going to be the part that's in the most positive x direction. The bottom is going to be in the most negative direction. All right, so we want to probably try to stay away from using top and bottom and just use positive and negative, because that works for both orientations. All right, so that means I could integrate between those two functions just by subtracting. But there's one slight catch. So notice here that this is a function of y, not a function of x. I can't integrate some function of x in terms of y. There are reasons you could do that, but it goes beyond what we're doing here and has other implications. Now, to do what we need to do, we need to turn these into functions of y, which is not a problem. It's not difficult to do, but we have to kind of go off to the side and make sure we get that done. So if I have f of x equals the square root of x, then that literally means to me f of x is defined as my variable y. So this is my strict relationship between the points in the domain, the x variable, and the range, which is the y variable. And I can hold that relationship true even if I solve for the other variables. So like, for instance, if I square both sides, I would end up with y squared equals x. But that, in fact, is a function of y. So I could say this is the same function f, but now it's in terms of the variable y. And similarly, g of x, which is 3/2 minus x over 2, can be thought of course, as a function y equals 3/2 minus x over 2. And then if I multiply both sides by 2, I would get 2y equals 3 minus x. Subtracting 3, that would give me 2y minus 3 equals negative x. And then dividing through by -1, I have x equals 3 minus 2y, because when I divide by a negative, this becomes positive, that becomes negative, so I can just reverse the order of that subtraction. Which tells me now the function g in terms of y can be written as 3 minus 2y. So now I have the top and the bottom of this rectangle defined as basically the rightmost point and the leftmost point with these new functions. So I can say my area then is going to be defined as the integral from 0 to 1 of the most positive, so the function g is the most positive here on this entire interval. So it's going to be g of y minus the most negative, which is f of y, dy, or the integral from 0 to 1, and g of y would be 3 minus 2y minus f of y, which is y squared. And now I have something that I can actually integrate and come up with an answer. Now, your calculator, when we're using fn_int, we can still use fn_int here. You can, when you go under math and 9, you can specify a different variable to integrate with respect to. So this is no problem. Integral from 0 to 1 of 3 minus 2. Y is not as convenient to grab, so you'd have to press alpha and the 1 to get a y here. All right, and then minus alpha 1 squared dy. There we go. All right, so then that's going to be needed to change into a fraction. So we get 5/3 as our answer here. And there we have it. Now, one other thing I'd like to mention is that when you're using the fn_int, it doesn't really matter what the variable of integration is when you actually do the integration. So you can change all of these to x's because it's a little easier to type in an x because there's this button right here. And if you want to do that, that's perfectly fine. Just make sure you change the variable of integration to x as well. You'll get the same response. It doesn't really make any difference. One other thing that you might need, however, is a bit of a review from trigonometry. I'll go ahead and put that in here. Is if your functions were given to you, like mine originally were given as functions of x, so I could draw this region fairly easily using the calculator. So if I didn't have the picture to start with, then I could get a fairly decent picture just using the calculator as such. And so you get the same region as here, and of course I could have used y=0 in there as well. Now the question is, had they given the functions in terms of y? So if they had already been solved, like f of y equals y squared, for instance, how would you graph that? Well, one thing is that students will try and do, which kind of works, but I'll explain why it's not great, is just change your variables to x and then graph it. But the thing is, as long as your graph contains a specific type of symmetry, everything's fine. But if it doesn't contain that symmetry, then everything's not so fine, because it's not like you're just rotating 90 degrees here, because that's what students will try and do, is just kind of graph it and then, rotate 90 degrees. So if I look at the screen, as if this part right here was actually pointing to the right, then yeah, that actually is the graph of x equals y squared, because it contains the symmetry necessary to be able to just rotate like that. But that's not actually what's happening. We're actually flipping about the line y equals x. And so when you flip about the line y equals x, that's what's actually happening with the change here in these variables. So it's a little trickier than you might expect. So that's not a great way to handle the problem. If you want to graph with functions of y, there's a couple of options. One, if you happen to have software that's able to just take an implicit function, which means you don't have to have your function solved for x or solved in terms of x in order to graph it, then you could use that to help out. But our calculators here, unfortunately, don't allow for implicit graphing. It's a bit more of an advanced technique of graphing, and so these calculators really just aren't powerful enough to do it. So without the ability to graph implicit functions, here's what we can do. You can switch into parametric form. All right, you might remember some parametric equations from trigonometry. And the thing is, parametric equations are a generalization of functions and really expand the number of functions that you can actually graph. Because parametric equations don't really care that you can actually write your function in explicit form, though it does have some restrictions. You do have to be able to do this technique, solve the equation for one variable. It doesn't matter if it's x or it's y, it doesn't make any difference, but you have to be able to solve for one. So here's how we could do this. When you go under y equals, whenever you have set to parametric equations, you're given two functions per graph, one for x and one for y. And these are in terms of the variable t instead of x or y. So to change a function into a parametric equation, it's actually quite straightforward. If, for instance, I wanted to graph f of x equals the square root of x. All right, so here's what I would do. So for the square root of x, since this is a function of x, x is my independent variable. So I just let my independent variable be t. And then the dependent variable, I just solve in terms of t. So the function, instead of writing it as the square root of x, I'm going to write it as the square root of t. And it means the same thing because t is equal to x. So if I substituted x into this equation, I would have y equals the square root of x. It means the same thing. When you look at the window settings, there's a few additional options. You have tmin and tmax. Those are pretty good to have set to -10 and +10 for most instances. And then the t-step at about 0.1 is pretty good. When you graph it, now of course you'll get the square root function. Okay, but let's try graphing in terms of another variable. All right, so let's clear this out. Oh, it won't let me clear one without remove. Oh, yeah, okay, there we go. Good. So in this kind of an equation, y is now the independent variable. We get to pick whatever we want for y, and that gets, and x is decided upon based on this particular function. So since y is the independent variable, you just set that to t. And then write the other function in terms of the function given, but switch your y's into t's. Because now, since y is equal to t, this is literally x equals 3 minus 2y. So, nice little trick, very handy. Allows you to graph equations very simply with being functions of y instead of being functions of x. So that will come in handy. The last thing that might help you through your homework, and I promise this is the last one, is intersection points. All right, so intersection points. If you needed to compute intersection points and you happen to have functions that are in terms of y, you can still do the same process. You can still set f of y equal to g of y and solve. So y squared equal to 3 minus 2y. If I solve this, I would have y squared plus 2y minus 3 equals 0. Or y and y, this would be 3 and 1, positive 3, negative 1. That's the factorization there. So we have y equals -3 and y equals 1 as solutions here. Now just be careful because these are y's and not x's. So there's an intersection between these curves at -3, y equals -3, and y equals 1. So we're definitely seeing this intersection here with y equals 1, but what they're saying is there's another one at y equals 3. And the reason is this particular graph has a lower portion, okay? And this line extends on this way. So there's going to be another intersection somewhere, and that's what's happening. So this is at some x value and -3 is what that's telling us. But our region is trapped between these two curves and the x-axis, so we know this is the only portion that we're interested in. So this part down here doesn't really make a lot of difference to us. All right, so solving for intersections works just the same. You just have to make sure you understand that you're getting y values as your answers instead of x values. If you need the x values, you certainly could calculate them. So for instance, like since we know f of y is equal to y squared, well then when y is equal to -3, then the x value would be -3 squared, which is 9. And when y is 1, the x value is 1 squared, which is 1. And that's exactly what we see right up here. This is the 0.11. So everything works the same. You just have to think in terms of the other variables.